In this video I'm going to be talking about Runge-Kutta methods. Okay, so Runge-Kutta methods, these are perhaps the most popular methods for solving ordinary differential equations. Okay, so Runge-Kutta methods, often known as RK methods for short. Okay, so these are involved, or these are interested in solving the ordinary differential equation y dash equals f of ty. Now y dash is the derivative of a function y, f is a function of the single variable t, and y is a function of t. Okay, so I'm going to go ahead and just write down what's called the general form of a Runge-Kutta method, which is yn plus 1 equals yn plus h times the sum of I equals 1 to s of bi ki. Okay, so yn, this is the current known solution for y. Yn plus 1 is some solution at a small step h forward along the in the t domain. Bi, well, these are just coefficients, and ki are what's called stage values, and the ki, these depend upon the ODE function we're solving. So this f of ty, ki is defined in terms of that. So we have f of tn, which is the current value for t, so yn is a solution at tn, and to this we add on some multiple of the step length h, so the multiple is ci, and instead of y in this function we have yn plus h times another sum, j equals 1 to s of a coefficient aij times kj. So these are what's known as stage values. Okay, so the s in the summations, okay, so this s here and this s here, this is the number of stages we have. Now the number of stages will depend upon your accuracy of your method usually. So what if we had 2 stages? So I'm going to write down these equations for 2 stages. So we have yn plus 1 equals yn plus h, and so the summation I goes from 1 to 2, so we'll have b1 k1 plus b2 k2. Okay, and the stage values, change the colour, we'll have 2 stage values, k1, so this will be f of tn plus c1h, so that ci there will become c1, and we'll have yn plus h times a11 k1 plus a12 k2. And so that's the first stage value. The second stage value is similar, except for where we have an I subscript, we've got a 2 instead of a 1. Okay, so those are our 2 stage values. So this is a the values of b1 and b2, c1 and c2. So so if I just underline, so the values of b1 and b2, c1 and c2, and our a values here, these are what define or what specify what our Runge-Kutta method is. It's quite common. Another way in which we could write down a Runge-Kutta method is in the form of a table. So what we have is this table with 4 sort of regions, and the bottom right region I'm going to put the b values. So here we've got 2 stages, so I've got 2 b values. In the top left region I'm going to put our c values, and in the top right region I'm going to write down the a values. Okay, so this is what's known as a Butcher tableau. So this is after the mathematician John Butcher. It's just an easier way or a quicker way of which we can specify a Runge-Kutta method without writing out all of the equations. Now, one thing I want to just point out about what I've got here is if we look at the expression for k1, we have a k1 on the left, so obviously this is the subjective equation, but we also have a k1 appearing on the right. Okay, so if we wanted to calculate what k1 is, it depends upon itself, and the same applies to K2. So you can see here we've got an expression on the right. So these are what's known as implicit equations. So a Runge-Kutta method of this form is known as an implicit Runge-Kutta method. So this is an implicit Runge-Kutta method, and this is often known as an IRK method for short. Now, implicit Runge-Kutta methods, because we have these implicit relations, they are actually a bit more complicated to solve than the other type of method, which is an explicit Runge-Kutta method. If we're presented with a butcher tableau, as we are here, we could easily tell whether we have an implicit Runge-Kutta method, because the main diagonal and upper triangular values in A are non-zero. So now I'm going to talk about explicit Runge-Kutta methods, which are the other type of Runge-Kutta method. So these are a lot more common because they're a lot more straightforward to actually calculate. So explicit Runge-Kutta methods are given the shorthand ERK for short. Okay, so what we're going to do with these is we're going to say if we let C1 equals 0, so we're always going to have C1 equals 0. That's some constraint we're placing on our method. I'm also going to say that Aij is going to be equal to 0 where I is less than or equal to j. Okay, so if we write down the Runge-Kutta method, so the updating expression for y is actually the same as the implicit method. Okay, so let's say we've got a two. Oh, got that wrong. Let's say we have a two-stage method, so similar to before. So b1 k1 plus b2 k2. So that's exactly the same as the one for the IRK method, but this time with k1. Okay, so ordinarily we'd add f of tn plus c1h. Well, c1 in this case is 0, so we just got f of tn. The second argument, well, that was yn plus h times our a11 and a12. Well, a11 and a12 will both be 0 because in this case I is 1 and j is 1 or 2. So that means we just got yn. So our first stage value is f of tn yn. Our second stage value, okay, that's the same as before, or similar to as before, so tn plus c2h, and we'll have yn plus h, and it was the sum of j equals 1 to s, so we'll have a21 times k1. Ordinarily we'd have a22 times k2, but because I is 2 and j is 2, the a22 would be 0. Okay, so that's the second stage value for an implicit Runge-Kutta method. Explicit Runge-Kutta method. Okay, so if we draw the butcher tableau for this, we have b1 and b2 down here. C1 is 0, and we'll have some value for C2, and the only non-zero element of A is A21. So this is what the butcher tableau looks like for a two-stage Runge-Kutta method. Okay, for a sort of general S-stage Runge-Kutta method, I'm just going to draw out the butcher tableau again. Okay, so got B1, B2, I'm going to go up to BS minus 1 and BS. Okay, and our C values, so we'll have C1 is 0, C2 and C3, all the way down to CS. Okay, so our A values, so A11 was 0, and if we go down the first column of A, okay, when we get below the main diagonal, we have non-zero values for A, so there's A22, all the way down to A S1. Sorry, that's A21 there. Okay, if I go across to the next column, well, A12 will be 0, so I'm just going to ignore that for now. A22 is also going to be 0, but A32 is non-zero. So I've got a non-zero on there, going all the way down to AS2. Okay, and this sort of carries on. This behaviour carries on, and what we have is we have this sort of lower triangular. Oops, just got the index wrong there. So it should be AS S minus 1. So we have this sort of lower triangular format to our A values. So if I just draw a border around our A, you notice there's nothing up here. Okay, well these are actually zeros, but I haven't written them for simplicity. So when we're presented with a butcher tableau, if it's strictly lower triangular, we have an explicit Runge-Kutta method, and if it isn't strictly lower triangular, we know we have an implicit Runge-Kutta method.